Swayamprabha. Digital India. Educated India.
Greetings to you all. We now move on to module 5 of this course, and this will end week 1 syllabus. We actually did a basic review water city transport equation. Then towards the end of last class we started doing something about classification of PDE. Review of the last few slides, we mentioned that elliptic PDE, they have no preference for direction for information travel or solution propagation. Hyperbolic PDE, disturbance propagates only at a finite speed in limited region, and today we are going to see hyperbolic PDE. We also went through parabolic PDE by taking example of diffusion equation, and we also explained we are not able to classify Navier-Stokes equation under any one particular category. It is a coupled nonlinear PDE with 4 variables, and we had seen this elliptic PDE by taking example of Laplace equation and Poisson equation, and then we observed the solution propagates in all direction, and this is a solution domain. And we did parabolic PDE by taking example of one dimensional diffusion equation, and we noticed that solution advances outward as shown here from the initial value, which IC is the initial values, and solution propagates in one direction outward, and such a solution or problem is called marching type problem or marching type solution. The third category, specifically called hyperbolic PDE, we consider one dimensional wave equation, and this is second order dou squared phi by dou t squared gamma squared dou squared phi by dou x squared, where gamma squared is some real constant, and we find out by fitting this with the generic equation, we find out the discriminant value b squared minus 4 ac, and we observe that it is greater than 0, and we classify for such situation equation is hyperbolic. As we have seen in parabolic PDE, this is also open ended nature of solution. That means it progresses and along the 2 characteristics curves. So, 2 boundary conditions are required because it is a second order equation. Now, we know that Navier-Stokes equation in full form does not fall under any one category. It is a coupled nonlinear PDE with 4 variables. It is parabolic because it has unsteady term. It is elliptic in space because diffusion term. On the other hand, you can simplify the Navier-Stokes equation for different situation, hence it will result in different nature. For example, if you consider steady viscous flow problem, then you do not have a unsteady term, you only have diffusion term, then the equation falls in the category of elliptic nature. We can also classify energy equation and simplify energy equation for different situation to get different nature of equation. So, solution require one set of initial condition and boundary condition at all boundary points for time greater than 0. Elliptic equations are generally very difficult to solve when compared to parabolic. So, usually what we do, we convert steady, for example, we have given here steady viscous flow equation. It is an elliptic equation, it is difficult to solve. So, we convert steady viscous flow or a steady problem elliptic nature into unsteady problem by adding time derivative term. Now, you march a solution until you get a desired solution, that is until you reach steady state condition. So, we pseudo treat the governing equation, change the form from elliptic to parabolic. The advantage is you have an initial condition, you progresses in time, it is only a marching in one direction, solution convergence obtaining is easy, and finally you get a steady state solution. So, this is one numerical trick that is followed to deal with elliptic nature of equation. Now, we define nature of equation. Before that we got all governing equation. The next step is to know something about boundary conditions. There are 4 types. The first one we see is Dirichlet boundary condition. Here we simply specify a definite value for the variable. So, for example, T, if you are solving temperature equation, T is a variable. So, you can specify T as a function of time, or T1 specifically a value T1 at x is equal to 0 on one side of the boundary, and T is equal to 2 T2 at another boundary at x is equal to L for all time greater than 0. So, specifying a particular value or a function, then it is called Dirichlet boundary condition. Initial condition, so you can also specify for time is equal to 0, T as a function of x for all x going from 0 to L. This means the domain, computational domain extends in x direction from 0 value to L, end of the domain is L. So, along that x direction specific value of temperature T is equal to 0 is given for time is equal to 0. This is initial condition, and for time greater than 0 at x is equal to L you have one value, at x is equal to 0 you have another value. So, you specifically give that value. Such a type of boundary condition is called Dirichlet boundary condition. Next is a Neumann boundary condition. Here we specify the derivative of the dependent variable. So, for example, you say dou t by dou x equal to 0 at x is equal to L. So, in the previous case we said t is equal to T2 a specific value. Here we are specifying the derivative dou t by dou x equal to 0 at x is equal to L for the same time greater than or equal to 0. Next is a Cauchy boundary condition. We have a mix of Dirichlet as well as Neumann type. So, for example, in this problem figure, along this boundary 0 to x we specify a derivative condition dou t by dou x equal to 0 on one side, on the other side we specify a Dirichlet boundary condition specific value, that is t is equal to T1. There is also another type what is known as a Robbins condition, where the derivative of the dependent variable is itself is specified as a boundary condition. So, in this case for example, dou t by dou x is given as t minus t infinity with some coefficients. So, this is what is known as a Robbins boundary condition. So, whenever you are going for a solution, you need to identify what kind of boundary condition you want to impose, whether it is a derivative boundary condition or a specific value of the boundary condition. Next, we also have to know what is the type of problem. So, there are 2 classification. One is a boundary value problem. Here independent variables are specified on all boundaries. For example, steady state heat conduction equation is given here, dou square t by dou x squared, dou square t by dou y squared equal to 0, and we know from previous class this is a Laplace equation and this is equation falls under elliptic nature of solution category. Now, boundary condition is specified on all the boundaries. So, in this the variable is T temperature and domain going from x as well as in y. So, you specify boundary condition in all of x and y. Next category is the initial value problem. Here at least one independent variables has an open region. Example, unsteady heat conduction problem, the same equation that we had seen before. If you add time derivative, it becomes unsteady heat conduction problem, and we know it is a parabolic in nature and the time starts from 0 to infinity range, and we specify temperature value. The temperature is a variable here. We specify a temperature value at time is equal to 0, and there is no value specified at time is equal to infinity. So, that is why it is called initial value problem. The one variable has an open ended solution. By now you have learned some aspects of CFD, and you will learn more aspects in future classes. After this, let us say you are ready to practice CFD. You have multiple options here. Either you write your own code, or you have inherited code from somebody or from open source, and another option to use any commercial software. Again, here again in commercial software all the features are available, but some micro programming may be required from problem to problem. Whatever the case, all the numerical strategies that you are choosing, for example, grid, order of accuracy, convergence criteria, matrix inversion procedure, time step and so on, all this have to be proved. Now, this stage of CFD is what is known as a validation case. For this validation, there are many test problems available. These problems are simple in flow or flow over simple geometries, and they have features representing features in complex flow, and these problems are tested and many results are available in open literature, either numerically or experimentally. So, one has to take these standard benchmark cases and first to prove all the numerical strategies that you have chosen for these problems, compare the results obtained by your own strategy against results available or reported in the open literature. That stage is what is known as a validation stage. Now, there are many test problems available. In this particular lecture, I am taking only few examples. Some of them represent internal flow problem, some of them represent external flow problem. The problems are flow in a cavity, flow through a backward facing step, flow past a cube mounted in a channel, and boundary layer problem. We will go into details of these flows from now. So, here we will see few examples. The first one I am showing here is a lid driven cavity. So, it is a cavity, the hash mark that is shown on the sides to represent it is a wall, and on the top there is a lid, and that is driven with the velocity u equal to capital U and v equal to 0, and the boundary condition imposed for this problem on all the sides, because we already mentioned it is a wall, on all the sides we put velocity equal to 0, that is u equal to v equal to 0, and such a boundary condition is called no slip. And we also know if you specify a value for the variable, it is called Dirichlet boundary condition. So, why are we interested in this problem? This problem is very simple in nature because it is rectangular, but there are many features that are present inside the problem appears in many other complex flows as well. So, there is a primary vortex and there are vortex in the corner. Depending on the velocity condition, the vortex will grow in size and you get a velocity distribution, etc. Depending on the velocity and depending on the size, then you can define the Reynolds number and it becomes either laminar flow or turbulent flow. The center of the primary vortex is offset at the top right corner for Reynolds number 100. Then it moves towards the geometric center of the cavity with increase in Reynolds number. So, the problem, though it is simple, by going on changing Reynolds number it becomes slightly complex and the way the vortex behaves also differs. Secondary vortices appear very near both right and left bottom corners. Next problem, test case problem, is usually the backward facing step. Here simplified, this is the inlet with velocity given as a parabolic inlet, and the top there is a wall, that is why you see the hash mark, and in the bottom there is a wall up to some distance, then there is a step, and then this step is also a wall, and then there is another wall on the bottom. So, because the step is facing the flow backwards, this is called backward facing step. The step has a height given by d and the channel, original channel width has a height h. Now, because with the wall on the top and wall everywhere, you specify a boundary condition u is equal to v is equal to 0, and if you look at the flow pattern, so flow separates at this corner and then it comes and reattaches. There is a recirculation zone and reattachment point. The way where it reattaches, what is the recirculation zone length depends on the Reynolds number and the flow condition. And similarly, you also get to observe there is also a secondary bubble on the top wall, and the size of the bubble, where the location of the bubble depends on the condition of the Reynolds number or any other flow condition. There is also another characteristics, what is known as the expansion ratio, which is nothing but the channel height to the step height, and that decides also some flow parameter. Corner vortex steadily evolves into a recirculation zone depending on the Reynolds number, and secondary recirculation observed on the channel upper wall. So, we have seen example for two external flows. The next example is flow past cylinder, circular in cross section, square in cross section. This falls under category external flow. So, here flow past a circular cylinder, depending on the incoming left hand side is the incoming velocity. Here what is shown here is a uniform velocity of u infinity, and there is a separation point, and in this problem separation point for this geometry is not fixed, it keeps moving, oscillating on the surface, and where it oscillates it depends on what is the condition here, inlet condition, and whether the flow is laminar or turbulent. Now, behind the geometry there is a famous one common vortex shedding, and you can have a situation where it is laminar boundary layer, transition and turbulent boundary layer, or it can be laminar boundary layer, laminar separation, laminar wake, or you can have a turbulent wake. Wake is nothing but the flow region behind the geometry. So, that is what is marked here, and it is unstable, and there is a shedding anti-symmetrically at regular intervals from the cylinder. Similar problem, but the geometry is square. The big difference between circular cylinder and square cylinder is separation points are fixed, that is at the corner, both top as well as bottom. Now, that decides the dynamics in the wake very differently, and flow separates from this corner, a separation angle and a shear layer separates and rolls into wake or vortex roll up and vortex shedding in the wake. So, for high Reynolds number, the flow separates at leading edge. Then third problem is a flow past flat plate, and that forms a boundary layer. In this problem that is shown here, incoming flow is a uniform velocity, and what is shown here is a plate representing flat plate, and so the flow starts from the leading edge. Initially it is laminar, then there is a transition, then there is a turbulent, and later we will see the definition of boundary layer thickness. So, whenever the velocity reaches 99% of the free stream velocity, then you call that as a boundary layer thickness. And the turbulent boundary layer again has subclassification, viscous sublayer, buffer layer, and so on. So, this forms another test case. The next problem is for a flow past a cube mounted in a channel, and you see two views of the same problem. Here is a channel, so upper is a wall and lower is a wall, and there is a cube that is fixed to the bottom of the wall, and if you see from the top and you see that it is mounted to the center in z direction, and u infinity is a velocity, incoming velocity, or it can also be a, here it is shown as a uniform velocity, it can also be a parabolic velocity profile. Now, why it is so complex? The geometry is very simple. So, the incoming flow will feel the pressure or the presence of the geometry, and there is a separation from the wall, and it forms what is known as a horseshoe vortex, and then behind the geometry it forms what is known as a arc vortex. So, prediction of this is a critical. Now, this geometry has many application. So, depending on the height to the side, it can be thought of as models of high rise building, or it can be thought of as chips on an electronic board. So, all these test problems are all very simple, but the flow features represent flow features noticed in many complex situations. So, whenever you write a code or whenever you set up a numerical scheme in a commercial software, you are supposed to validate by taking benchmark cases, and many literatures are available to get results and to confirm the result that you obtain against results reported in standard literature. So, with this we come to end of week 1. In week 1 we have seen all the important topics, and in week 2 we will actually start CFD techniques. Thank you.